Hi everyone. I'm just trying to. Oh yeah. So it seems to be working. Where is the chat? Okay. So I hope everybody can hear me. Let me know if you can't. Now that you see me speaking. Otherwise, we are just ready for questions.
Hi, Professor. I got a quick question.
Uh-huh.
I was wondering if I'm allowed to actually record office hours and upload them to YouTube, where YouTube will provide the subtitles for everybody.
Oh, I mean, yeah. I actually like the only ones that like cannot do that are us, because if we do that, then we are like officially obligated to subtitle it correctly, and I mean that would be a lot of work to do for office hours. So to kind of maintain like an interactive format for them and stuff like that, we basically do this, and we cannot record them, but pretty much any student can record the office hours. That said, there is a configuration somewhere in here that allows students to record this, and unfortunately, like there is no way to actually kind of just make the default like students can record. So I basically have to I have to find it, and actually like every time we do this, I have to toggle that like students can record button. So I'm just trying to find it now. It used to be. Yeah, it's not here anymore. They've messed with WebEx since I last did this. So let me just. But yeah, I mean, I have nothing against you, like recording it and then posting it. Just trying to assign privileges.
All right, thank you. Don't worry about it. I actually can record it here on my
No,
desktop, so
it's
I
like
got it.
it's totally ridiculous. Basically, used to be in the kind of I can change the participant privileges to basically allow anybody to record, but now it's not there anymore. Okay, I'll read the manual for. I mean, it's so basically like you don't see a record button over there on the screen where you see like who's talking and stuff. There is a button for like muting the mic. There is a button for.
No, on the top menu, I see under meeting recorder
No, 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 no,
settings.
no, no, no. This is kind of near the bottom of the screen, basically, where you have the your video currently, or my video that you're seeing. There should be like when you move a mouse over it, there should be like kind of round buttons for like muting the mic and stuff like that. And one of them should be the record the meeting.
No, I don't see that.
Okay, which ones do you, I mean? But you do see the other ones, right?
Yeah, I see all the other
Yeah,
little
yeah, okay,
circles.
okay. So that means that for some reason it's I mean it's always been like that. It's like disabled by default, and then I can enable it, but I cannot find where to like enable it. Allow participants. Okay. Yeah. Okay. So I'll try to figure out. I mean, it used to be that basically, like, there was a setting there in the settings that I could allow participants to record, but it's not there anymore. And I thought maybe that's because by default now you can record, but apparently not. So I'll try to see like is there a way to enable that? Okay, so I mean, I cannot do it now. I'll have to like kind of read the documentation for this, or kind of the support forum and stuff like that. But I'll figure it out after these office hours. Okay, so there is two of you. There are no questions other than this one, but it's a good question. Thank you for like reminding me, because I was really thinking now that the thing is not there anymore, that that means that like it doesn't need to be enabled anymore, but apparently it just moves somewhere else.
I do have a question.
Uh-huh.
I forget which lecture it was. I believe the one titled Memory. But you were talking about how SRAM and DRAM is actually laid out with transistors, and DRAM with one transistor and a capacitor. And there was a row buffer which holds the values. So I was wondering how the row buffer is actually built. Is it kind of using the 6 transistors like SRAM?
Yeah. I mean, so basically, the row buffer is like the normal flip-flop kind of essentially the structure of the DRAM and SRAM basically is like the cells that keep the bits are designed a little bit differently from like what you would do on a normal flip-flop that you're using to implement your processor or something like that, right? Because the flip-flop essentially is not really designed for being really small. It's designed to be a good flip-flop, right? So basically, when you have like a pipeline latch or registers in a processor and stuff like that, those are basically designed to be really fast, right? And behave well in terms of kind of their flip-floppiness, and you don't want them to have like weird behaviors that would require you to put additional logic around them to do something, right? But for SRAM, for both SRAM and DRAM, essentially, there is a trade-off between them behaving in a very simple memory-like way, and so the trade-off is essentially between kind of them just being flip-flops like, and basically being really small, so you can cram a lot of them onto a surface area. Because for both SRAM and DRAM, you kind of want to put as many of them as you want per unit area, and you need a lot of them. So it actually matters. I mean, it matters enough that they're small that you were willing to sacrifice both speed and also how do you read them and write them. So for SRAM, the design basically kind of goes just a little bit away from flip-flops and uses essentially either a 4 or a 6 transistor implementation. The 6 transistor implementation is basically almost exactly like a flip-flop. The 4 transistor cell is like a kind of like a deficient flip-flop that basically you need to wait on a little bit longer, and when you're writing to it, you need to do slightly more weird things. Whereas DRAM kind of goes all the way and says, I don't need it to behave like a flip-flop. If it can, if there is anything that can remember a bit for a while, I'll find a way to work with it. So essentially, the cell is just a single transistor with basically a capacitor buried underneath to keep the charge and thus hold the value. And the idea is that for both DRAM and SRAM, rather than them being accessed as kind of like a normal flip-flop, which means basically you just kind of read the value of the output of the thing, there is essentially a surrounding piece of logic that for a whole memory array that basically allows you to actually successfully read and write the array that you have. So the idea is that the cells in the array need to be really small, and then whatever these cells cannot do that is needed for reading and writing, there will be logic that kind of sits around the array that will essentially implement that functionality. So the row buffer is part of that functionality, basically. Like one of the things that the cell cannot really do is quickly provide the output and route it all the way to kind of the edges of the array. Because basically the cell, being designed to be so small, cannot drive a lot of current into the bit lines, and that means that if we just let the cell pump the charge into the bit line, for DRAM, that's going to be a problem because the cell will totally drain and only raise the bit line just a tiny bit or lower it just a tiny bit depending on the bit. For SRAM, the cell actually can do this, but it's going to be really slow because the cell is still so tiny that its transistors are just not going to supply a lot of current. So they're going to be basically raising or lowering the voltage on the bit line really slowly. So what you have is essentially you have this sense amplifiers basically that are essentially trying to say, okay, I see the bit line moving slowly up or slowly down, and I'm going to amplify that, right? And then once that is amplified, basically you don't want to, for every piece of the line, for every piece of the row that you're reading, you don't want to repeat that sort of procedure, right? You need to kind of latch that into something that will properly remember it, so that essentially subsequent reads can go there rather than access the array again, which is going to be slower than if I just read from flip-flops. And also for DRAM, you need to actually remember it in a way that allows you to write it back, because you've just lost the actual values from the cells in that row once you read the row, because the cell is now totally drained in order to raise the bit line by a tiny bit, which means that you kind of, once you do the read, you actually have to properly write the contents back into the row of cells, and essentially for that you need to remember what was there, which means that you need the row buffer to remember that. But because the row buffer, there is essentially only one bit in the row buffer for the entire column of cells, the row buffer doesn't need to be tiny. I mean, its purpose is essentially to be a good row buffer, not to be totally tiny, which means that you can implement it with like proper, flip-flop like, implementation. Essentially it's like a 6 transistor plus maybe 6 to 8 transistors, depending on how fast you want it to be and stuff like that. The only kind of unnatural thing about the row buffer is that you try to lay out the design so that essentially the row buffer can neatly sit beneath its row, so that basically you still need to pack the the bits of the row buffer in a way that kind of neatly is laid out, so that essentially you don't have to route a lot of wires to it, because let's say the row buffer bit is like 7 bits wide. Well, that means that you kind of have to find like a routing for every row to go to its row buffer. It would be the neatest if you could kind of design the row buffer to be every bit is like one column wide, in which case essentially the row buffer just sits underneath its row. Typically, you cannot do that because the row is designed for density. So I mean, the cells in the matrix of the memory are designed for density, which means that they're really narrow compared to like a normal flip-flop. So typically, what you have is some sort of an interleave thing where, like, let's say that your row buffer bit is like 2 array bits wide, which means that you kind of put 2 behind each other, like kind of like this, and then essentially bit 0 goes here, bit 1 goes here, and you have to route it, but then you just repeat that thing for every pair of bits in the row or something like that. So there are some concerns about the kind of arrayness of it and stuff like that, but by and large you design these things to essentially behave like flip-flops.
Okay, and if I understood correctly, basically because of the size of it is the reason why and the fact that there's many rows of DRAM that can map to one row buffer. That's why we don't just use row buffers for all of in place of DRAM. We still have DRAM because they're smaller.
I mean, even for SRAM, you design the cell to be as kind of regularly square as you can, and as narrow and short as you can. So basically, the cell for SRAM is still, the priority is on making the cell be neatly arrayable, such that the array is compact, right? The row decoders, which is basically how the stuff where you essentially give the address and the row number, and it basically activates the particular row. The row decoder, there is only one for the entire memory array, right? And then the sense amplifiers and the row buffers and the column decoder, those are, again, there is only one of those for the entire array. So essentially what you design the array for is to pack as many bits as you can into kind of the matrix of it. And then these surrounding logic things, if they need to be a little bit larger, that's okay, because basically it's like every bit of the row buffer, essentially, if you make it a little bit larger, it only extends the overall array a tiny bit, because it's not added to every bit in the memory array. Whereas the actual cells are like that. Like you have 1,000,000 cells, that's, let's say, 1,000 by 1,000 array. That means that, like, if the cell is a little bit larger, that's like 1,000,000. That increases for 1,000,000 cells. Whereas if you have the row buffer be a little bit larger, it has, let's say, 1,000 elements, 1,000 bits. that means that essentially, even if you double the size of the row buffer, it's still like its size is tiny compared to the array. You can think of it as basically there is a matrix with kind of stuff along the left edge and stuff along the bottom, and that stuff along the left edge and bottom has some size, but that size is kind of tiny compared to the size of the actual array, which means that for the matrix, for the cells, you kind of worry a lot about how densely you can pack it. The other stuff, yeah, the size kind of matters, but even like a significant increase in size of that is not going to dramatically impact how many of these arrays can you pack onto a chip. So there the priority is on essentially doing it fast and doing it well and stuff like that. For the cells, the priority is in kind of packing them as densely, which means that designers are willing to sacrifice the kind of cells performance for the sake of packing more of them, even if that means that like I mess up the cell such that I essentially need to now make the other logic around the kind of the row buffers or sense amps or something a little bit fancier, because kind of the cell becomes crummier. That means the sense amp needs to be fancier, but that's actually usually a good trade-off, because by making the cell crummy, if you can actually reduce it by like 5%, that's a 5% improvement in density. Whereas you double the size of the let's say sense amp and the row buffer, that's like maybe a 1% increase in the overall size, simply because they're already comparatively small relative to the how much area is occupied by the bit cells themselves. Now for processor design, like the registers and stuff like that, there the trade-off is a lot different, simply because keep in mind that for both caches and memory, you have kind of like cycles to access them, right? Whereas for these structures that are kind of inside the processor core, you at best have like a cycle or two to access a structure, and if you need more than one cycle, you'll need to pipeline the thing and stuff like that. So there you are significantly more concerned about speed, which means you make it to be a proper flip-flop and to be as fast as it can, even if it's maybe occupying much more area than it could if I made it be a kind of slow cell that just remembers what I put in it. So as you can see, like everything in computer architecture is this way. I mean, there is no like this is how we do memory bits. Like depending on where exactly is this bit. You have like many different designs for like how do you store a bit, because you have like the DRAM style bits, you have the SSD style bits, you have the kind of SRAM style bits, you have bits that are used for kind of flip-flops and stuff like that, you have bits that are used for latches, which are kind of deficient flip-flops, because that some things that flip-flops are designed to prevent will not happen and stuff like that. So sometimes, for example, you actually have like a faulty flip-flop that you save the transistor and your flip-flop doesn't really work as a flip-flop anymore, but that the aspect that transistor is there to prevent from happening will never happen because of the rest of the design.
Okay, thank you.
Yeah, sure. Same things actually happen with logic. Basically, we talk about, like, for example, 7 nanometer or 10 nanometer and stuff like that, but in reality you size the transistors for basically speed and essentially what they can drive, as in how much output current they can produce. So for example, a transistor that needs to feed a lot of inputs, I mean, like its output is connected to a lot of inputs, you'll design it to be bigger, because so like you can make it small, but then it's going to take a lot of time to charge all of those wires and stuff like that. So you design it to be bigger so it can drive more current. So essentially it's going to be bigger, more power hungry, and slower than it would be, but the end result is something that overall is faster than if you design the tiny one. Because yes, it can kind of, a tiny one can like get the value to its output, but then because it decided essentially now I'm outputting a zero, but to actually make it zero, it has to essentially consume all of the charge in the wire that it's connected to, and if it's really small, it cannot do that quickly. So the overall time for when my gate gets inputs to where the gates connected to it can read the output of it is actually dependent not only on how fast your gate is, but also how much current it can drive. So if you have a thing that only feeds one input, you can make it tiny and fast. If you have something that feeds a lot of inputs, you actually don't want to make it tiny. You want to make it beefier, just because the overall time is going to be essentially dominated by just charging the output or discharging the output, and so on. So the layout of the actual like physical layout of the transistors and stuff like that is not just like all the transistors that are the same. Actually, they're all sized differently based on these kind of trade-offs between essentially the speed of the transistors themselves and the speed at which they can pump charge into their outputs. But I mean, all of these things are kind of like for the like the layout engineers and the layout tools to take care of. So pretty much, what we architects usually will do is we will say, okay, I want the output of this to be connected to that, right? And then it's on the tool to decide what's the optimal sizing of the gates, transistors, and stuff like that to kind of minimize the overall time. Or even the tool may decide, you know what, this transistor, even if it's much slower than the usual transistor in producing the outputs, it's still gonna make it for the end of the clock cycle because it's on a short path that doesn't really have a lot of stuff going on it, and it will design to essentially decide, yeah, this thing is like connected to 10 other things, but even if it's 3 times slower, it's still not gonna affect the clock cycle time, so I'm gonna make it small. Another thing that is connected to 10 things is maybe on the critical path of the clock cycle, and I'm going to make that one much bigger so that it can essentially have the optimal timing that is needed. So basically, the tool not only needs to decide, what size would be optimal, but also, do I even want the optimal size? Because for some things, I don't need to optimize timing essentially, because the timing is already kind of has some slack essentially. Like this thing basically is feeding one of the paths that can be slowed down without affecting the overall clock cycle time, simply because there are other longer paths. So normally when you do architectural design, you kind of don't really worry about that. You kind of design your processor and stuff like that, and then you kind of run these tools and stuff to basically give you like what would be the actual timing and what would be the actual clock cycle and so on. And then if the tool says, oh well, the clock cycle is like 5 megahertz, and okay, I was kind of hoping for 1 gigahertz, what's going on? Then you say, oh, but the tool says that there is this long path, which means probably you should be pipelining this or something. Essentially, the processor is trying to do too much the way you designed it, it's doing too much in this cycle, in this part of the processor. And then you kind of go back and kind of work on it. In reality, the situation is that you kind of don't try to avoid things like that from the get-go, because it's really difficult to kind of re-pipeline the processor if you've designed it. But yeah, the only time when you kind of are worried about how fast things can be and what the tools can do and stuff like that is if you really have some sort of kind of, I know this is the critical path, and I'm really trying to kind of squeeze that one into as little time as possible. But at the architectural level, the way you address these issues is basically by saying, okay, this needs to be done over 2 cycles. It cannot be done over 1 cycle, because if I try to do it in 1 cycle, it's gonna take too long and stuff. And sometimes there are disappointments. Sometimes the designers actually, do kind of what they thought was right and stuff like that. They design everything, they lay it out, they finally run the layout tools, and they discover that the frequency is like way smaller, lower than what they planned for. and that's when you kind of go back to the drawing board. It's like, okay, what's the problem? But the tool also tells you which paths, I mean, which chains of logic are the problem, which means now you know which aspect of your processor you probably need to worry about, making more pipeline or stuff like that. But those kinds of changes are really tough to make, because you can imagine, if I need to add a pipeline stage, a lot of things need to change. I mean, you need to change forwarding to now account for this one extra pipeline stage. Your stalls are going to be one cycle more, so it's probably going to also not only affect the clock. I mean, kind of, yes, I can improve the clock cycle time, but what it's going to do to my number of stalls and stuff like that. So the overall performance actually may be affected significantly, even if I do the extra pipeline stages and stuff like that. So you kind of try to avoid problems like that, but they do happen. And when they do happen, it's like a 4-month delay in the release of a processor, because it's a lot of work. You kind of have to go back to almost like high level design, and then kind of update all the steps that you've done kind of since then, and then like rerun the tools. And then usually that introduces bugs and stuff like that pretty much every time you have a human doing something, there's going to be bugs. So essentially those kinds of things are way more problematic than kind of the tool sizing transistors differently and stuff like that, because the tool essentially will automatically choose the sizes and stuff like that in a way that preserves the correctness of the design and tries to optimize for performance. We humans can do better at optimizing for performance, but at the cost of usually introducing logic bugs and stuff like that. Okay, so any more questions? Yeah, nobody's asking anything. Okay, I have a question. So, so from basically when I release the midterm grades, essentially, I'm not actually sure what students see. So from the questions in Piazza, I kind of inferred that you can actually see the comments for the individual questions. But do you actually see the sub score? So basically, there is like an overall score for the quiz. There should be also for each part of the quiz, there should be kind of like a separate score, and then there should be kind of like a comment for, so basically like for question 2, there should be like, this is how many points out of 8 you got, and then there should be a comment saying why you lost the points you lost. And I'm not sure if students can actually see both of those things, like the sub scores and the comment, or do you just see the comment for each part and the overall score?
I think I see everything. I see for each individual question the amount that I got and the amount total,
Okay,
and then
okay,
at the bottom.
That's what I hoped you will see, because that way it's kind of clear how you lost the points, and how the but Canvas has so many configuration things about this thing that it's kind of hard to come up with like the right settings that will actually let students see that without seeing things that they shouldn't see. Okay, so there was a question. I'm not sure how SMT and cache work with virtual memory. Oh, that's a kind of good question. So basically, the question is, when you have cache coherence, essentially when you have cores that basically have their own individual caches and then they're kept coherent, how does that all work with virtual memory? And the answer is basically that as far as virtual memory is concerned, the coherence simply doesn't know that there is virtual memory. Essentially, as far as coherence is concerned, all addresses are physical addresses, and this is how it really works, right? So every core, when it's accessing its own level 1 cache, is also doing address translation, right? And all of the so basically you can look up your cache using virtual addresses and stuff like that. But if it's not there, or if you need to do a coherence action, that action is done with the translated address, right? So in a typical processor, there will be something like, virtual index physically tagged L1 cache, which means that by the time you're done accessing your L1 cache, you already are operating with a physical address. So if you have a cache miss, you use the physical address to kind of send a request for the data. If you have a coherence action, like for example, I need to, for example, having something in a shared state, and I want to upgrade to modified, you send a request for that block using the physical address. So as far as the coherence protocol is concerned, basically all addresses are physical addresses. Essentially, the only part of the memory subsystem that has to do anything with virtual addresses are essentially the level 1 caches. And that dramatically simplifies the coherence, because essentially in the physical